Hi everyone, I am Arnab. I am a PhD student at IIT Indore and I will be talking about the continuum science we have been doing with uGMRT, observation of LS northbound field, which is also a SK India. uGMRT is also a SK India Pathfinder. So it is done with some collaboration with many other people from across India. And so there are many precursor telescopes like MWA, LOFAR, ASCAP, etc., along with GMRT, which has a some dedicated continuum survey of different spectroscopically and multi-frequency rich deep field. And they have a common goal to image the wide area of the sky very deeply to understand the evolution of galaxies over cosmic time and how cosmological parameter and large scale structure that drive it. So there are several questions people want to answer with this deep survey, such as what type of objects dominate the source counts at low fluxes, are there undiscovered populations? What causes the scatter between different surveys at low fluxes? Do we need better simulation to guide research in this area? And how do environment and large scale structure affect the evolution of radio sources? So I'll be talking about this our findings and try to connect with these questions with what I am showing here. So what we know 12 years back and 2008 that we know from the SCAT simulation, which is a square kilometer array design survey, that at low redshift, the star-forming galaxies are most dominating. However, at higher redshift, the AGNs are most dominating counterpart. And in the right, what I show here is the DNDS plot, that is the distribution of sources as a function of flux density. These are normalized DNDS plot, and as we can see in the low flux density regime, that is below zero point 0.1 millijansky at 1.4 gigahertz, there is a lot of scatter from the observation, and of the order of let's say there is a scatter of 2 to factor of 2 to 3. So many people said that so this is basically due to the small sky area we are probing here, basically due to cosmic variance. But however, these are unable to explain this large scatter. Also, Condon et al. Proposed that there are many corrections people made during in this plot, like resolution bias, clean bias, Eddington bias, and etc. And this bias may give some scatter, but that is again it's not possible to give this large amount of scatter at low flux density regime. So something is going on at this low flux density regime, which we want to understand with current generation telescopes. So this is not clear what causes the scatter between these different surveys at low fluxes. Now, this in the left panel, I show you the plot from Bongini et al. 2013 that gives you the fraction. In the y-axis is the fraction of sources, and in the x-axis is the flux density at 1.4 gigahertz. And as you can see, that for the fast, this is the limit for the fast and NVSS all-sky survey at 1.4 gigahertz. And when you go deep with current surveys, and SK will maybe probe much deeper here, and what we can find that the star forming galaxies are becomes dominating this green line below 1.1 millijansky at 1.4 gigahertz. However, the AGNs are decreasing, the population of AGNs are decreasing. However, the key thing to notice is that there are two different kind of AGN. One is radio quiet and another one is radio loud. So radio quiet AGNs have started dominating the population below zero point 0.1 millijansky, and however the radio loud AGN which are continuously decreasing. So this is the scenario that we understood from the observation of ECDFS at 2013. However, the challenge is that how to distinguish this radio quiet AGN with the star forming galaxies, because they have many properties which are same, like radioluminosity and spectra and all other stuff. So this is a headache. So what we can do, we can study a field with multi-frequency observation, and we can start from radio, X-ray, IR, and all other probes of the same field to understand how this evolution happening for star forming galaxies and radio quiet AGN. Now, this is a current picture at 2018. This is from taken from Tandani et al. So as we can see that the many observation, this shows a plateau or maybe a increasing source density at below 1 millijansky at 1.4 gigahertz, and there is a comparison with all other different observation, and we found that this black line is the prediction by square kilometer array design survey, which is back in 2008. Now, the recent observation shows that there is a significant increase in the source count below 1 millijansky. And in the right panel, if we see that there is a clear indication of increased source population below 1 million C, which we try to understand with a more deeper survey. And they propose that Pranjal proposed that a 1.4 gigahertz large field points towards an excess with respect to ST model. The ST model is basically the SCATS model below 400 microyans, or say let's say 1 million. So the question is that, do we need better simulation to guide research in this area? So do we need more updated simulation over the scare, and are there undiscovered population? So are we missing something since we are limited by sensitivity here? So what our observation? We observed a alias Northman field with uGMRT both in wideband correlator mode and both softer correlator mode. I will be talking about the wideband correlator result. And we have taken the data from 300 to 500 megahertz with 8K channels and 2-second integration time. And this is the total observation time is 25 hours, where the 13 hours is the on-source integration on-source time of the alias Northman field. So alias Northman field has a excellent multi-wavelength coverage also. So the inner black circle is our field of view with uGMRT at 400 megahertz. And as we can see that we have a huge multi-frequency coverage both from Panstar, Sawyer, SARS, Sparks, Subaru, etc. And the outer curve is from LOFAR. So this is the LOFAR field of view at 150 megahertz. So this is our result. So we calibrated the whole data set from 300 to 500 megahertz. This is the continuum image at 400 megahertz. We reach one of the deepest RMS at this band, which is 15 microjoules per beam. Note that we have not done any direction dependent calibration here. This is only the direction independent calibration, and only the phase calibration, phase only self calibration has been performed. And the color bar show gives you the RMS range from -1 sigma to 10 sigma, and this white dashed curve is the primary cut we made for this observation. And after getting this image, we ran PyBTSF to extract the sources, and we got 2,500 sources from this within this primary being cut. So in terms of RMS, where are we? So this is taken from the recent LOFAR survey of LS Northman field. So this point is from our data our survey, and this is at 150 megahertz. So note that. So this we are not far away from the expected RMS, and this is just the extrapolation of the RMS from LOFAR to our frequency band. And also note that LOFAR has already performed direction dependent calibration, and they have 164 hours of observation, whereas ours is only 13 hours of observation on source before flagging, and we have not done the direction dependent calibration yet. So we are not far away from the the RMS sensitivity, which we can reach with more with the direction dependent calibration. So next we check the flux density offset, and just note the top right plot here. So we compared our flux density values of sources with many different surveys of the same field, let's say 16 megahertz, and also we cross-checked with NBSS and FAST survey, and we found that this is quite consistent with other survey, and there is no significant flux offset of the sources for our field for our observation. Then we checked the offset, the positional offset by comparing the position of our sources with the fast and GMRT 16 megahertz. As we can see, the mean offset is less than 1 arc second. Note that the pixel size of our observation is 1.5 arc second. So the maximum deviation, the mean offset is less than the pixel size. So we think that our positional accuracy is also fine. Then we find out what is the normalized source count as a function of flux density. As you can see, these red points are our data points. As we can see that there is a clear flattening signature we found below 1 millijansky at 400 megahertz. And we overplotted here different source models, all-square source models, that is SKAs by Willman et al., and also the T-Rex model by Bonaldi et al. As we can find out that this flattening model is clearly giving an excess source population over the SKA. SKA is this black line, and we are actually following the T-Rex model. So as we can conclude from this graph here that SKA is predicting or giving less number of sources as it should be than the observed population. at the in the low flux density regime. So here I plotted the different source population from different surveys by different groups, and as you can see, this is also consistent with this magenta one. Magenta one is the basically Cosmos survey at 3 gigahertz, which goes very deep in at the frequency, and we find that this is exactly consistent. However, there is a clear excess by the 1.4 gigahertz previous finding by Hopkins et al. So something is going on at this low frequency regime.
Arnab,
So
you have 2 minutes.
okay, so I should mention this here. So now what one has to do, that in the y-axis this is the ratio of the IR flux, IR to radio flux as a function of redshift, and there is a clear evolution of that. And when you incorporate that evolution, you see that there is a clear excess of the model prediction, and that is actually consistent with the observation. So and this evolution has been implemented in T-Rex model by Bonaldi et al, and this is currently consistent with the defined findings. And this is taken from T-Rex, where left-hand plot, the top plate is 150 megas to 15 gigas, and they have already also showed that their model is quite consistent with the observed finding. However, at 150 megas, this flattening has not been seen yet till 2019, but recent low-far observation at 150 megahertz by in 2020, they found that there is a clear flattening due to the excess population of star-forming galaxies and radio-quiet AGNs in this regime. So next, we have also find out the clustering of sources. People have done it with the SDSS or the galaxy survey. However, the advantage of radio is that the radio wavelength is not obscured by dust, and also we can survey a large volume area with the radio observation simultaneously, and we find out what is the clustering properties of the sources. That is the excess probability of finding a source within a separation over the Poissonian distribution, and we find that our result is consistent with the previous survey. However, it is the Cosmos survey shows you lower clustering. Basically, they are probing the faint galaxies which are residing in lower massive halos, which are less clustered. And we identify the sources in star forming galaxies and AGNs using the radio luminosity, and we find that the star forming galaxies are dominated at the low flux density regime, whereas the AGNs are dominating at the higher flux densities, at the higher redshift, sorry, had a higher redshift close to 1. And then we find out what is the spatial clustering using the redshift distribution, and the angular clustering we use the Lindbergh inversion, and we find out what is the clustering properties of AGN and SFGs. We find out that AGNs are strongly clustered, where the clustering length is 7.3 MPC inverse, whereas for star forming galaxy it is less, 4.62. That tells you that star forming galaxies are hosted by less massive halos, and whereas AGNs are hosted by large halos which are strongly clustered than SFGs. And here I plotted the evolution of clustering length as a function of redshift, and along with the observation of multi-frequency observation from previous survey. As we can see that there is the expected evolution is slow as a function of redshift. However, it has a significant deviation from the SKA survey, which is the lower curve, which tells you that the halomas description they have used is not quite appropriate in comparison with the observation. For AGMs, we find that this is mostly consistent with the FR2 galaxies, FR1 galaxies, and this is also consistent with the previous findings also. So these points are our findings here. Then I plotted the bias. That is the bias of the star forming galaxy AGMs with the underlying dark matter distribution, and we found that so the bias is as a function increasing as a function of redshift, and then there is a plateau here, and then there is a constant of this. But however, we do not have any probe using radio or other multi-frequency survey in this regime. However, we can say that this is the star forming galaxy, which are, if we compare with the underlying SCAT survey, we can say that this is hosted by less massive halos, whereas for AGMs, these are hosted by larger halos of the order of 10 to the power 13 solar mass. Then these are some sources which has spectroscopic information available, and Akriti Sinha et al, another student from our department who is studying the multi-frequency properties of these sources. And she also used the multi-frequency diagnostic to understand to discriminate the AGMs and to understand the radio loud and radio quiet population of the sources. And I will skip this thing. And last, I want to mention that our main goal is to study the H1 power spectrum at the posterior epoch using this wideband correlator. we incorporated the foreground avoidance technique to estimate the H1 power spectrum. This is at redshift 3.58. And we put an upper limit, which is a stringent upper limit, although this is a factor of 3 larger than the prediction. However, this is quite close to the expected thermal noise, and this is the multi-frequency upper limit at redshift from redshift 1.96 to 3.58. And we also try to understand what is the constraint on omega H1 and DH1 parameter product of that at this redshift, and this is still 2 orders of magnitude higher than the expected values at this redshift. So I'll leave it this summary. Thanks.
Thank you, Arnab. We can take a quick question. So again, people on Zoom, you can raise your hand and ask the question. So Arnab, a quick question on this plot. Can you, like, how many hours of observations do you need to actually reach the theoretical signal?
Okay, so we predicted that that would be more than 3,000 hours.
Okay.
So this is before flagging, yeah.
I think Prajwal has a question. Prajwal, please go ahead.
Can you hear me?
Yes.
Yeah, so
Yes, Prajwal, we can hear you.
I may have missed it, and you may have said this already, but do you have polarimetric data as well?
Sorry, which data?
Polarimetry.
Yes, yes, but we have not done it yet.
Do you have plans? And
yes, yes. Another student from IIT BHU, we along with Prosunda, tried to calibrate the polarization calibration, but we are not successful as of now. So I don't know. Maybe in future we can do it.
I see. Okay, thank you.
Okay, I guess we have to move on now.